All right. So this brings me now to the third part of the bilinear transformation design, which was actually the first part, right? So we already have done, if you know the analog filter design specifications, how to use a low pass prototype filter to convert it into another analog filter. We already have done that if we have the transfer function for the analog filter, how to convert it into that of a digital filter. So that we've already done, right? What we have not done is how to get the corresponding analog filter specifications, right? So let's do that. Let me just pull up my notes. Okay. For that, we will start with the bilinear transformation. The bilinear transformation that you saw over here, right? This guy. So let me just write it down here. So S equals 2 over T z minus 1 over z plus 1. Right? This is the binary transformation that we have. Okay. Now, what we will be doing, we'll be understanding a phenomenon which we also later call as the frequency warping phenomenon. Why is it the case, or what is that, right? Now, you remember, if you are in the S plane, let's say this is sigma, this is g omega, right? This is the frequency axis. This is, let's suppose, the S plane. In the Z plane, where does the frequency axis map to? Uh, the frequency axis, this one. The circle itself, right? It maps to the circle. And you can assume that this is a circle, although it looks like up here, right? So this vertical axis maps to the circle. Okay. Question. What is the frequency range for the case of this analog frequency? This one, like this vertical axis, right? It goes from where to where? Yeah, it goes from negative infinity to positive infinity, right? So the analog frequency, let me denote it by omega A, right? It comes from a range that goes from negative infinity to positive infinity. Clear? However, in the case of the digital frequency, let's suppose, if you talk about the normalized radian frequency, this frequency is pi, this is minus pi, right? But if you talk about the frequency, the corresponding frequency in radians per seconds, this frequency is omega s over 2, which is omega s the sampling frequency in radians per seconds, and this frequency is minus omega s over 2. So the digital frequency, on the contrary, comes from minus omega s over 2 to plus omega s over 2. The analog frequency goes from negative infinity to positive infinity. The digital frequency comes from the range minus omega s over 2 to plus omega s over 2. Right? Now, that means we are mapping an infinite range of frequencies to a finite range of frequencies. Or, on the contrary, when we go from the digital frequency to analog frequency, we are mapping a finite range of frequency to an infinite range of frequencies. Now, this mapping is highly nonlinear. For that reason, let's suppose a frequency of, let's say, 10 radians per second, right? For the digital frequency, will not be the same as the 10 radians per second in the case of the analog frequency. So that mapping, is nonlinear, and that nonlinearity we call it something known as the frequency warping phenomenon. Yeah, and we can find the relationship between the frequencies from this bilinear transformation. And how can you do that? If you are on the the S plane, what do you replace S with to get the frequency values? J omega, right? So you replace S with j omega, to get the frequency values, right? And let me call it j omega a, right? Because we are talking about the analog frequency. And in the case of the z domain, to get the the location of the z plane that contains the frequency values, right? What do we replace z with? E to the j capital omega, where this capital omega is the normalized frequency in radians, right? And to get the frequency in let's say radians per seconds, right? We can just replace z with e to the power j omega dt. So we do these substitutions to get to the location of the corresponding planes that represent the frequency values. Yes or no? Yes? Sure? Sure. Clear, right? So what we will do to relate the frequencies on the, for the analog frequencies and to relate the frequency to digital frequencies, we'll just replace s with j omega a and we'll replace z with e to the power j omega dt. Clear? Clear? Let's do that. So then in place of s, I'm writing j omega a. So j omega a equals 2 over t. Z is, I'm replacing with j omega dt minus 1 over. Why do I not use j omega, the normalized radian frequency, right? Because I want to find the relationship in terms of radians per seconds between the two, right? This one will tell you, if I just replace it with omega, it will give me the relationship of what analog frequency in radians per seconds correspond to what frequency, normalized frequency in radians. Yeah, so just to have a relationship between the radians per second frequency in the analog domain to radians per second frequency, the corresponding radians per second frequency in the digital domain, just to have that. So for that reason, I'm replacing that with e to the power j omega dt. Yeah. Tell me the difference again between omega d and omega a. Okay, so this omega a is the frequency on this vertical axis in the S plane. That means the corresponding analog frequency. Omega d is the corresponding digital frequency in radians per seconds, right? Now, the analog frequency, you see the range goes from minus infinity to plus infinity. The digital frequency, on the contrary, goes from minus omega s over 2 to plus omega s over 2, where omega is the sampling frequency in radians per seconds. Yeah? So here we are mapping, if we are trying to find the relationship between these two frequencies, this relationship is highly nonlinear. Why? Because we are mapping an infinite range of frequencies to a finite range of frequencies. And to get to that mapping, I'll just use the bilinear transformation and replace s with j omega a and z with e to the power j omega dt. Clear? Clear? Okay. And then from here, rest is like, just algebraic manipulation. I'll just take e to the power j omega d t over 2 common. I will have e to the power j omega d t over 2 minus e to the power minus j omega d t over 2 over, I can take the same thing common here, e to the power j omega d t over 2. Inside I will have e to the power j omega d t over 2 plus e to the power minus j omega d t over 2. So far so good? Yeah? Clear? Clear? Okay. And then I have on this side, I have j omega a, right? Oh, sorry, j omega a. And I move this j to this side. So I have omega a equals 2 over t, and this will cancel. I have e to the power j omega d t over 2 minus e to the power minus j omega d t over 2 over j times e to the power j omega d t over 2 plus e to the power minus j omega d t over 2. By the way, what is this thing? It's a tan, right? Why? Because cos of x equals e to the power jx plus e to the power minus jx over 2, right? Sine of x is e to the power jx minus e to the power minus jx over 2j, right? And then tangent of x is sine over cos, sine over x over cos of x, right? And then this is sine is e to the power jx minus e to the power minus jx over 2j, and times I have 1 over cos x, which is 2 over e to the power jx plus e to the power minus jx. So this, sorry, I forgot this is 2j, right? This 2 will cancel, right? And what do I have? I have e to the power jx minus e to the power minus jx over j times e to the power jx plus e to the power minus jx, which is tan of x.
So it's exactly the same, there's no consequences.
Sorry?
So it'd be exactly the same.
Yeah, so here in place of x you have this omega d d over 2. Yeah, so this whole thing will become tangent, right? So this whole thing, so then I will have just omega a equals 2 over t tangent omega d t over 2.
So this is what causes morphing, right?
Yeah, so you can see, the relationship between the digital frequency and the analog frequency is nonlinear because of the tangent, right? And from here, you can do some manipulations to show that omega d is equal to 2 over t tangent inverse omega a t over 2. Yeah, I'm sure. You can verify it. Does that make sense? Clear? Yeah. And you can verify, for example, let's say, you can verify, let's suppose omega a, right? We said that it goes from minus infinity to plus infinity, right? So let's see, let's say, if omega a is plus infinity, right? If omega a equals plus infinity, right? So then what do we have? We have omega d equals 2 over t tangent inverse infinity, right? So what is tangent inverse infinity? Is pi over 2. Yes, yes. Then you have 2 over t, which is times pi over 2, right? And then you have, yeah, so t is essentially, it's what is fs, right? So 2 pi fs, right, essentially is equal to omega s, right? And what do you have? Fs is like essentially 1 over t, right? So you have omega s, right? So 2 pi over t, then you have times 1 over 2, right? So 2 pi over t is essentially the sampling frequency in radians per seconds. If you have sampling frequency in hertz, right? So fs, so 2 pi fs is equal to sampling frequency in radians per seconds, right? And then in place of fs, fs is just same as 1 over t, which you have over here, right? So just replace fs with 1 over t. You have 2 pi over t equals omega s. So then this whole thing is omega s over 2. So that means when omega a is plus infinity, omega d is what? Omega d is omega s over 2. Where omega s is what? What is omega s? Huh? Sorry?
What was the question?
So, okay. I'm saying when omega A is plus infinity, that means analog frequency is plus infinity, right? The digital frequency is omega s over 2. And omega s is the sampling frequency in radians per seconds, right? So that is the relationship, right? So that means this guy, when this is at plus infinity, I am at omega s over 2. When I'm at minus omega s over 2, I'm at minus infinity. Clear? Yeah, makes sense, right? And that relationship is highly nonlinear. Why? Because of these equations. Questions till this point? All good? Yeah? Okay. All right. So let me just show you some slides. Yeah. Okay. So this is if you plot the omega A and omega D on these axes. So let's suppose you plot omega D versus omega A. You will see that, as omega goes to infinity, omega D, that saturates at zero point 0.5 omegas or omega over 2. Right? So if you was plot values of omega A, right, omega D versus omega A, right, given by this expression, right, you will see that this is going to saturate at zero point 0.5 omegas. Make sense? Clear? Clear? So then, in summary, how does this bilinear transformation look like? Let me just show it in the form of a PDF document because that's good. All right. So if you want to design the bilinear a filter, digital filter using bilinear transformation, right? So what do? You start. Let's suppose you take the example of a low pass filter, right? Just for an example. So you need to design a digital filter with the low pass with the cutoff frequency of omega d radians per second, right? So low pass digital filter. What do? You see this particular omega d corresponds to what corresponding analog frequency? How? By from the relationships that we just derived. So you just plug in omega d here, you'll find out what the corresponding omega a would be, right? That is from here. And then what you do, you just take the low pass Wernicke filter and convert it into the filter of the frequency that you got over here in this step, right? And then once you have the the analog filters transfer function, you convert that transfer function into the digital filter transfer function by applying the bilinear transformation. So again, you start with the digital filter design specifications, right? Let's suppose here we are taking the example of a low pass filter. Let's suppose you need to design a low pass filter with a cutoff frequency of omega d radians per second, right? Then what you do, you see you pre-warp the frequency. That means you find out the corresponding analog frequency that corresponds to this particular digital frequency. Once you get the corresponding analog frequency, you take a low pass prototype filter, get the transfer function of another filter of the specification that you got in this step. And once you have the transfer function of in this step, that means the transfer function of the analog filter, convert it back into digital filter by applying this bilinear transformation. The next slide is the same thing, exactly the same thing, but written in words, right? Step one, you just pre-warp the digital frequency to get the corresponding analog frequency. And then what you do is, by the way, for low pass and high pass filters, you will just have one frequency. For the band pass and band stop filters, you will have two frequencies, right? The corresponding to the lower analog frequency, the lower cutoff frequency and the higher cutoff frequency. You do the same thing for both. You get the center frequencies by finding the geometric mean of the lower and higher cutoff frequencies and the bandwidth, right, which is the difference of the two. And then just take the low pass prototype filter, just transform it to the corresponding filter design specifications that you get over here. And then from the resulting analog filter transfer function, you convert it back to the digital domain by just applying the bilinear transformation. Clear? Yeah. So let's do an example and then we'll conclude this topic.
Is this the last topic?
I mean, then we have just one topic. I mean, it's about the design of, design using the pole zero design method. Design of the infinite impulse response filters using the pole zero design method. For that, we'll just take two examples of a peaking filter, a notch filter, a band stop filter, and the band pass filter, right? That we'll see. Just place poles and zeros certain places to get a resulting filter, right? Okay, so let's do a quick example and then we'll conclude. Any questions so far apart from this? All is well. All right. Sorry. Okay, why did we follow that strange thing, right? Because to make you understand the frequency pre-warping, I needed to make you understand the bilinear transformation, right? And then and why did we need bilinear transformation was to convert a digital filter to the analog filter to a digital filter, right? So for that reason I started with the second part and then the third part and then the first part, right? Yeah, the order of explanation was just to make it easy for you guys. That's it. Okay, good. So let's do an example. So given a low pass prototype filter, which is hp of s equals 1 over s plus 1, use BLT. It's not the same as JLT, which is Jumeirah Lake Towers. That's a different thing, right? You don't have Jumeirah Lake Towers, right? It's not. It's different. It's bilinear transformation, right? Bad joke. Sorry. Yeah, there is a sandwich, right? Yeah, it's lunchtime as well. Right, I'm getting hungry. Use BLT to design a digital. I think it's a Subway sandwich, right? Yeah. Okay, now I'm really hungry. Digital infinite impulse response low pass filter. Low pass filter with a cutoff frequency. Seriously, I don't know why it's flickering. This makes sense. With a cutoff frequency. Seriously. With a cutoff frequency of 15 hertz and a sampling rate of 90 hertz. Okay. Step one, you pre-warp the digital frequency to get the corresponding analog frequency. So, but before that, those equations are in radians per seconds, right? So here the frequencies that you have are in hertz. So first you will convert them into hertz. So the corresponding digital cutoff frequency is 2 pi fc, which is going to be 2 pi times 15, which means it is 30 radians per seconds. 30 pi radians per seconds. Okay. So then we can, and then at the same time, the sampling rate fs is 90 hertz. That means the sampling interval is 1 over 90. So this is the information that we have from the question. Yeah. So first up, we just get the corresponding digital frequency, sorry, analog frequency. Omega A equals 2 over T tangent omega dt over 2. Clear? Yeah. So from here, omega d in this case is 30 pi radians per seconds. 1 over t is, sorry, t is 1 over 90. This will be 2 times 90 time tangent 30 pi times 1 over 90 over 2. And that comes out to be 103.92 radians per second. A common mistake which people, particularly students, do when solving these questions, not to check the calculator is in radians or degrees, right? Uh, that happened some time ago with NASA people, right? The scientists were using the, I think, SI units, and
Using the imperials.
yeah, the engineers were using the imperial, right? Or yeah, I think, yeah, that was the case. And then the calculations did not match. I think they were sending a mission to Mars probably, or Moon somewhere, right? And just, it just went way off, right? So that makes, it gives you the idea that units are really important, because that can cost a lot of money.
Isn't the easiest way to mitigate this just writing the units next to the whatever you write?
That's true, actually, right? But yeah.
Okay.
But anyways, all right. So that was step one, right? So you got the corresponding analog frequency. Step two, you take the prototype filter, which is 1 over s plus 1 in this case, right? Apply the transformation that would convert it into another low pass filter, because you need to design a low pass filter. And transformation for that is you need to replace s with uh, s over omega e. That means you need to replace s with s over 103.92. And then when you do that, I'll wait for this to come back, right? So just have h of s is going to be 1 over s over 1 over 3.92 plus 1. And then when you simplify this is just 1 over 3.92 over s plus 1 over 3.92. So this is the corresponding analog filter with a cutoff frequency of 103.92 radians per second. Clear? What would be the last step? Convert it into a digital filter. Using what? Bilinear transformation, right? So just replace S with 2 over T, Z minus 1 over Z plus 1. Yeah, and Z minus 1, T is 1 over 90. This is going to be 180 times Z minus 1 over Z plus 1. Right? So just need to replace S with that. And when you do that, right, just plug it in this one, right? So you have h of z then equals 103.92 over, then you had the s over here, so 180 times z minus 1 over z plus 1 plus 103.92. Yeah, and then I will do something here which you cannot do right now. You will do that in the exams if I ask this question. So after doing some simplification, right, I'll write the final result. The final result will come out to be 0.3660 plus 0.3660 z to the power minus 1 over 1 minus 0.2 679 z to the power minus 1. So this is the transfer function of the resulting filter with the cutoff frequency of 15 hertz, low pass filter with cutoff frequency of 15 hertz or 30 pi radians per second. You can verify that by plotting it. But since this filter is of order 1, it may not give you a great, frequency response. Clear? So again, what do? We started with this information. We needed to design a low pass filter, a low pass infinite impulse response filter using the binary transformation design with a cutoff frequency of 15 hertz and the sampling rate of 90 hertz, right? And we were given this low pass Brodai filter. So what did we do? In the first step, we found the corresponding analog frequency, right? But then to do that, we needed to find first digital frequency in radians per seconds. We were given the frequency in hertz. So that's just 2 pi times this, that's 30 pi radians per second, right? Similarly, if the sampling rate was 90 hertz, the sampling interval would have been 1 over 90 seconds. Use that information to pre-warp the frequencies to get the corresponding analog frequency. Corresponding analog frequency came out to be 1 over 3.92 radians per second. And then in the next step, we use the low pass Brodai filter to convert it into another analog filter of the cutoff frequency of 1 over 3.92 radians per second by just applying S with S over omega A. And that was this filter. And then the final step, we apply the bilinear transformation. Just replace S with 2 over T, Z minus 1 or Z plus 1. And then after doing some simplifications, this is the final result that I get. Clear? Any questions? All good. You can also verify, or you can plot the frequency response using the frec-z function that we studied earlier, right, in MATLAB. Clear? Any questions? So this concludes the binary transformation, topic. You can do your, other examples in the book, like for example, for high pass filter, the band pass or band stop filter, that will follow the exact same, procedure. Exactly. Just you will use a different kind of a transformation over here, right? And yeah, that's it. So, and in the case of band pass and band stop filters, you will have just two cutoff frequencies, the lower and higher cutoff frequencies. Clear? Any questions? All good. So I will.